Yeah, okay. So what I'm going to do in the first hour is to prove the denseness of minimal surface, and then I'll state the equidistribution, make some conjectures about it, and then in the second hour I'll prove the equidistribution. So I guess the advantage of being one of the last people to speak is that pretty much all the motivation has been given, so I can just remind the concepts and start the proof. Okay. So the theorem I'm going to prove first, this is joint with Kairi, Fernando, and myself. And the theorem is, so the setup is, we take some closed Riemannian manifold whose dimension is between 7 and 3. And the statement is that for a C infinity generic set of metrics G, the union of all closed embedded minimal hypersurface is dense. Minimal hypersurface with respect to the metric G is dense. Okay. So I guess the conjecture here. Yeah, thanks. Cheers. So the conjecture is that this result should be true without the generic assumption and without the dimension restriction. So this should be true for all n greater or equal than 2, even without the generic assumption. Without the generic assumption. So on any manifold, the set of all closed embedded minimal hypersurface should always be dense. So let me introduce some key definitions, and they're going to be with us for the rest of the 2 hours. So the first, I just call this S of G. This is just to prevent me from always saying closed embedded minimal hypersurface with respect to G. So this is just the set of all closed embedded minimal hypersurface with respect to G. And the second set, which is going to be important, V of G, this is a set of all stationary varifolds whose support is a closed embedded minimal hypersurface with respect to G. So the way we say this, we can imagine this is just the sum, any linear combination of embedded minimal hypersurface where the coefficients are integer, where Ni is an integer and sigma I is an embedded minimal hypersurface for all I between L and 1 and for all L an integer. Okay, so we should, this is lives in the space of variables, but we can just imagine it as being Radon measures where the measure is given by integration. Okay, and then this makes sense there. That's right, yes. That's right, thanks. Where sigma I intersects with sigma j is empty if I different from j. Yeah. Okay. So the support always has to be smooth and embedded. Okay. And so there's another important concept given. Oh, okay. So there's an important space here, which is the space of mod 2 n cycles. Mod 2 n cycles. And the important theorem here is due to Almgren, is that the cohomology ring of this space with coefficients in Z2 as a single generator. We write this way, okay? And using this generator, we can talk about case sweep-outs. So if p is an integer, we say that p of p, this is the set of all maps phi from X into the space of mod 2 cycles, such that so the first condition is that the map phi is continuous in flat topology. The second condition is that if we pull back the generator and we do its p power, pth cup power, this is going to be non-zero in HPX of Z2. Okay. So there was an important condition which I should have put before this one, is that X is a finite dimensional complex. And there's a technical condition, which I'm not going to say what it is. I mean, I'll state it, but don't write definition. Is that phi has no concentration of mass. This is a mild technical assumption. So this is the set of all p sweep-outs, and then we define the volume spectrum. Then the definition is that omega p m, this is the nth among, I take a p sweep out, I maximize the mass of the element, and then I minimize among all possible p sweep outs. So this is the, and this sequence is the volume spectrum. Is the volume spectrum. So the two key properties of the volume spectrum, so the first is that it obeys a universal law. This is the Vi law. Yevgeny spoke about this 2 weeks ago. This is Lyokumovich, Fernando, and myself. And so the statement is that there exists some universal constant, alpha n, so that the limit, so that for every Riemannian manifold, if I do the limit when p goes to infinity of the p width of m, here I put like this to remind myself that's with respect to the metric G. And if I put with respect to the appropriate power, this is going to be the universal constant times the volume of m with respect to the metric G raised to the power n over n plus 1. So this is a nonlinear analog of the Vi law for the energy. So this is the first key ingredient. And the second one, this is the min-max theorem. So this is due to Pitts, Shane-Yao, but Fernando and I also had a contribution here. Well, what? Oh yeah, sorry. Oops. Yeah. I apologize. Let's get the names right. Shane Simon, Pitts, and Mark, and myself. And the statement is that for every integer p, there's an element in that set V of G, so that, let's write p, so that the p width of M with respect to the metric G. This is equal. And now I should write the mass, but the shorthand notation we use, we just put brackets. So this means the mass. It's the n-dimensional volume, sigma p, and the support, the index, the Morse index of the support of sigma p is less or equal than p. Okay. So the first is that the sequence of numbers obeys a universal law, and the second one is that the sequence of numbers is realized by the area of an element whose support is an embedded minimal hypersurface. Okay. Okay. So now let's prove the theorem here. Let's start the proof. And so we're going to need two lemmas, which will be important for what will follow. I'm going to give them numbers because later on I will say lemma 1, lemma 2, lemma 3, and whatnot. Okay. So the first lemma says that the width divided by the growth rate, they are uniformly Lipschitz in terms of the metric. So is that given a metric G, there is a C0 neighborhood of G and some constant, some positive constant that depends on this neighborhood, so that if I consider the p width of M with respect to some G prime, and I divide by the appropriate growth rate, and I subtract the p width of some other metric G prime prime divided by the appropriate growth rate, and I take the absolute value, this is less or equal than this constant C, the C0 norm between G prime and G prime prime, put like this. Yeah, and this for all P in N and all G prime and G prime prime on the neighborhood. So the rescale width, they are uniformly Lipschitz. Okay. So this is a common feature of essentially any spectrum. So usually when we define spectrums, it's a common feature that they tend to be Lipschitz continuous with respect to the metric. So let's prove that briefly. Okay.
So does C depend on P a priori?
No. So that is the point. No. C will not depend on P. C will depend on G. But it will be independent of P. So they are uniformly. That's right. Yeah. There you are. Yeah. Yeah. So that's the crucial thing. Yeah. So I'll just write the two key inequalities that give the proof, and then the proof can be derived easily from these two inequalities. So let's just do proof. So the two key steps, the key steps are so the first one is to show, this is an inequality, is that if we have a map phi from X, if we have a P sweep out, but for the formula I'll write being a P sweep out, it does not matter, then the supremum when X belongs to X of the mass of phi X with respect to the metric G prime, this is less or equal than, now I'll write the maximum of all points y in M and v in Ty M, where v is non-zero. So in here, what I'm going to maximize is the quotient between G prime and G prime prime of G prime VV over G prime prime VV. We take this number, we raise it to the power n halves, we subtract 1, and so I'm going to need here the whole board here, times the supremum when x belongs to x of the phi of x, but now with respect to the metric G prime prime, plus the supremum of x belongs to x of this guy. Okay. So this follows simply just by comparing the. This follows simply just by comparing the metrics. Okay. And we write this way. Okay. So this is the first identity. And the second identity is that there exists some constant just depending on this neighborhood u that we can choose. So u will be all metrics such that all metrics h, so that h is less or equal than 2g and greater or equal than g over 2. Okay. So that will be a constant just depending on this neighborhood, so that the p width of m with respect to a metric g prime over p to the n plus 1 root, this is greater or equal than c1 the inverse and bounded by c1 for all g prime in the neighborhood u. Okay. So if we put these two things together, then the proof follows, because the first thing I do is I just take this element to be the one that is almost gives me the width for G, the p width of G prime prime. And then, of course, this guy, by the min-max definition, is greater or equal than the p width of G prime, and this is equal to that. So this just gives me this inequality multiplied by the growth of this element. But from this second fact, we have that this element grows uniformly for a neighborhood of G with the n plus 1 root, and so we can get that. I mean, it's nothing special. So the lemma follows from 1 and 2. Lemma follows from 1 and 2. Okay. So there is a second lemma which we are also going to need. Okay. Okay. Let me give the second lemma. So the second lemma, is this white? No. A yellowish. Okay. So let me write the second lemma. The second lemma is going to be a bit more general than what we need to prove that theorem, but it's going to be needed for the second hour. So the second lemma is that if we are given L minimal embedded hypersurface with respect to some metric G, which may intersect but are all distinct, then there exists a sequence of metrics Gi converging to G in C infinity, so that each of these minimal surface is also minimal with respect to the perturbation and become non-degenerate. So that two things are going to happen. One, sigma j is minimal with respect to the perturbation G of I. This is for all j between L and 1 and all I. And most importantly, they are all non-degenerate. So sigma j are non-degenerate right, with respect to gi, again for all j between well and 1 and all I. So non-degenerate means that the second variation formula will have no element in its kernel. Okay. So what we're saying is that if you have L minimal surface for symmetric G, if one of them has a kernel on second variation, you can always do an infinitesimally small perturbation that they all become non-degenerate. Okay, so it's a simple perturbation lemma. So let's do the proof. Okay. So the first thing is to find the point xj on sigma j, so that a ball around this sigma j, this xj never intersects any other sigma k. If k different from j. Okay. So we have the minimal surface. This could be sigma 1, sigma 2, and we take here the point x2 and here the point x1. And now, having that, I can make this delta smaller if necessary. So then I consider the following function. So let me see, fj. This is going to be defined on the neighborhood of the point xj into the real numbers. And fj of x is the sign distance to sigma j. So here there's a ball of radius delta there, such that given a point, it just measures the distance. So the level surface are just the parallel surface there and the parallel surface there. So sign distance means that one side is positive and the other side is negative. Okay. So this function is smooth if delta is chosen sufficiently small, and the key thing is that its gradient is just the normal vector. Okay, after you choose it. Right. And the second function is a cutoff function. The second function is a cutoff function, let's just say phi j, again from this tiny neighborhood, is cutoff function that will look like this. Let me just write it. So here's 0, here's delta halves, and 2 delta thirds, and delta, and it's going to be 1 all the way up to delta halves. Then it goes down to 0 and then becomes 0. So this is going to be phi j. Okay, it's a cutoff function. And now we make the this degeneration will be a conformal deformation. So the degeneration one does is we take what did I call it? No, it's important. Let's call it psi to be equal to the sum when I goes from 1, or j goes from 1 to L of phi j fj squared. And given this, I define g of I to be exponential minus 2 psi over I times g. Okay. So g of I is a tiny conformal perturbation of g, and as I goes to infinity, of course, g of I goes to g. And now what we have to check is that the sigma j are also minimal surface with respect to this metric. And if we do the second variation, if there's an element in the kernel, that element will eventually disappear. Okay, so let me write it.
Is the definition? Oh, it's a multiple, not a...
Say it again.
Is phi multiple ft squared?
Yeah, phi, let's see. I don't have any phi. I have psi over I.
I mean, in the definition of psi, is this a multiplication?
Of psi, no, it's a sum when j goes from 1 to L, and I sum phi of j against fj squared.
Just a multiplication.
Yeah, multiplication, yeah. So this is a function which is 0 outside the balls, and the crucial property is that it's 0 on the minimal surface, and the gradient is also 0 on the minimal surface. Okay. So the crucial, so this function, it was chosen this way to have the following three properties. So the key properties are the properties are, one is that psi is 0 on sigma j for all j. The second property is that the gradient of psi is also 0 on sigma j for all j. And the third property is that the Hessian of psi evaluated on the normal of sigma j, this is equal to just 2 phi j. I mean, this is a simple computation. Okay, so these are the crucial properties. This is for all j less or equal than L, less or equal than 1. Okay? So in particular, the fact that the function vanishes along the minimal surface and its gradient vanishes, it says that that perturbation is second order, and so if it's a second order perturbation, the sigma j should still be minimal with respect to the matrix G of I. So let me just write that here. So let's write it there. Okay. So 1 and 2 implies that sigma j, now I want to say sigma j is minimal with respect to G of I. So because I have that notation S of Gi, I can just write this for all j less or equal than L in 1 and all I in N. This is saying that they are still minimal with respect to the perturbation. Nothing can change. But now from the second identity, from the third one, we can do the second variation of these guys. And so we can see that for all x a normal vector field, okay, we have that the second variation of sigma j here in the direction of x with respect to the metric G of y. So it's going to be the second variation with respect to the metric G plus another quadratic term. So this is an identity. It's going to be the second variation of sigma j with respect to the metric G. But now we get another term, which is 2n over I, the integral on sigma j of the function phi of j. Okay. So these guys are minimal surface, so they are critical points for the area. We can do second variation. The second variation with respect to the metric Gi equals the second variation with respect to the metric G minus this quadratic term, which is there just because the Hessian of the perturbation is given by that. So this is a explicit computation when one can do this. So you can check this identity, and from this identity we can deduce the result. So let me do that. Okay, so let's do this. Okay. So we can now deduce the result. So Q of j is the index plus nullity of this quadratic form. Okay, to be the index of sigma j with respect to g plus the nullity of sigma j with respect to g. Okay, so it's the index plus nullity. So the one thing we obtain immediately is that the qj plus 1 eigenvalue of that quadratic form, eigenvalue of this quadratic form with respect to g has to be is strictly positive, right? Just because qj takes care of all the negative eigenvalues plus all the zero eigenvalues. So of course the next one is strictly positive by definition. Okay, so this guy is positive. And now there's when we compute, we know that the eigenvalues can be given by a min-max formula using the Rayleigh quotient. And so if we use that min-max characterization of the eigenvalues and these identities, so let's call this star. So star plus the min-max characterization okay, so I don't know how to write this. Plus min-max formula for eigenvalues implies the following. So I know that my qj eigenvalue has to be less or equal than 0. So I have a family of qj plus 1 parameters in which the quadratic form is not positive, in which this quadratic form is not positive definite. Because the quadratic form for the metric gi is the quadratic form for the metric g minus a negative multiple of something which is almost the identity, then if I have a q parameter family, if I have a q-dimensional plane in which this guy is non-positive definite, then for the same q-dimensional plane, this is also non-positive definite. And actually, if this is non-positive definite, this becomes strictly negative because there's a term there. And so one thing we get is that the qj eigenvalue for this quadratic form, sigma j, with respect to the metric gi, this has to be less or equal than minus some universal constant over I, because there's an I there. Okay, this is all I in n and all j. Okay. Now we can do the same reasoning for the qj plus 1 eigenvalue. So if I take a plane, if I take a qj plus 1, actually, so if this is qj plus 1, you have to take a qj plus 2 dimensional plane. And if I maximize the quadratic form for this term, then I know the maximum for the quadratic form is going to be greater or equal than the maximum for this quadratic form minus some term of this form. Now, the maximum for this quadratic form has to go higher than this eigenvalue. And so we get that the qj plus 1 eigenvalue for this quadratic form has to be greater or equal than the qj plus 1 eigenvalue of this quadratic form minus some constant that goes like 1 over I. Then we get this. And we also have 2. And 2, the identity is that the qj plus 1 eigenvalue for the quadratic form of sigma j with respect to gi, this has to be greater or equal than the qj plus 1 eigenvalue with respect to the metric g minus the same constant C1 over I. And so this is strictly positive if I is sufficiently large for all j. Okay. So I get that if I is sufficiently large, the Qj eigenvalue is strictly negative. The Qj plus 1 eigenvalue is strictly positive, and so there's no nullity. Hence, the nullity for the second fundamental form of sigma j with respect to gi, this is equal to 0 for all I greater or equal than 1. Okay. Was this okay here? It's okay. It's I mean, I don't know. I just want to cross the T's and dot the I's, right? Do everything. Okay, so let's. Okay, good. So we have lemma 1 and lemma 2. We can prove the theorem now. Okay, yeah. Okay, so we can prove the theorem. Okay. Okay, so let's do the proof of theorem. Okay. So let's take U containing M an open set. Okay. And so given this open set, I have a set which I call curl M of U, where this is a set of all matrix G, such that there exists a minimal surface with respect to G, such that the minimal surface intersects U. Okay. And there's one more condition, and sigma is non-degenerate with respect to U, with respect to G.
Sorry,
Yeah.
may I go back one
Yeah,
second
sure,
there?
sure.
So there's just a little point. If you want to do for L minimal surface at a time, when you argue with the Q-dimensional plane, you could have that the vector spaces generating it are just supported away from the support of phi j, right? So you don't get
What?
So you were arguing with the min-max story, right?
Yeah, it's visually on so the perturbation. The plane, the dimension of the plane depends, of course, on J, right? Yeah.
So
Yeah.
There is one point that Andrea didn't mention that
Yeah.
we use also unique continuation for eigenfunctions.
Yeah. So this is,
That's
I think
right.
this is the story that
Ah,
because
okay,
the point
yeah,
is
that's
that
right.
you fix your Qj and you
Yeah.
argue for
That's
sigma
right,
j, right? And so the in metric G you got something less or equal than 0,
Yeah.
but the other term a priori doesn't give a negative amount, right? It gives something less or equal than 0.
No, but this term is strictly positive on the. Oh, okay, that's right. Yeah. So I mean, the eigen. That's right. That's right. Yeah. So I was using an electron notation. Yeah, you're right. Yeah, it's okay. Yeah, you're right. Yeah, it's okay. Yeah. So we take this set mu, and there's another simpler set, which is mu star, where this is just the set of metrics. Is the same set, but without the non-degeneracy condition with respect to G. Okay, so this is the same set, but without there exists some sigma in SG, such that sigma intersection with U is different from 0. Okay, so this set is all metrics for which I find a non-degenerate minimal hypersurface that intersects U, and this is the set of all metrics for which I find a non-degenerate minimal surface which may or may not be non-degenerate that intersects U. Okay, and so the advantage of taking this set over that one is that the set mu is open, so this is easy to see using the implicit function theorem. because of the non-degeneracy condition. Okay. So now the goal is to show that mu is dense. Mu is C infinity dense. So if true, then we choose a basis of open sets, we choose a basis of open sets and set M to be the intersection of I of all M U of I, which is going to be bare generic or bare dense. So it's a countable intersection of dense open sets. So it's called bare generic. And of course, if a metric belongs there, it means that for every open set, you can find a smaller one. You can find a UI which is containing that open set, and so you can find a minimal embedded hypersurface which passes through the smaller open set, in particular passes through the big open set. Is bare generic, and G and M implies that the union of closed minimal embedded minimal surface, minimal hypersurface is dense. So the thing to check is that the set MMU is dense. So the second lemma implies that to check that M of U is that we might as well check only that M star of U is dense, that implies that M of U is dense by the lemma 2. So lemma 2 implies that suffices to see that this set is dense. Is dense. So let's just, so suppose not, which means there's symmetric G, which does not belong to the closure of M star closure. Let me just write. In the C infinity topology. So with this metric G, we do the following. So now we do a tiny perturbation that just to increase the volume on the open set U. So let's do the picture. There's my manifold. There's this set U. And I take this metric. This metric has the property that no minimal surface with respect to this metric ever intersect U. So here are all the minimal surface. And moreover, if you do a really tiny perturbation of this metric, that will also be true for the perturbed metric. So in particular, we just choose some function of compact support, some smooth function of compact support on U, which is non-negative, non-zero, and out of this function take G of t, which is this conformal deformation. Okay. So the first remark is that if I choose t in a really tiny neighborhood, then no metric GT will also belong to the set mu star. So first remark is that there exists a epsilon such that GT does not belong to mu star for all t between epsilon and 0. Okay? Just because I'm assuming that G is not in the closure and G of t is a C infinity perturbation. So the second remark is that, and this is crucial, is that G of t, let's see, how did I write this? That's fine, yeah. Is that G of t equals the metric G on M minus U. And so I know that all minimal surfaces with respect to g of t never intersect u. And so, but outside u, the metric g of t and g, they are the same. So what this means is that the minimal surface with respect to g of t and with respect to g, they have to be the same. And so we just write this way. All t. Okay. The third remark, and this is also crucial, is that I can assume that the metric G is bumpy, meaning there's a theorem of Bryan-White where it shows that being bumpy is C-infinity generic. And so I can assume that the metric G has a property that every minimal surface is non-degenerate. So without loss of generality, G is bumpy. Okay? And so if G is bumpy, then it's a theorem of, it follows from a theorem of band-sharp. So sharp compactness implies that all minimal surface with respect to the metric G, the set is countable. And so in particular, so the set of all minimal surface with respect to SG to the metric G is countable, and because they are the same, this implies that all minimal surface with respect to the metric GT, they are also countable. Is countable because they are the set is the same. Okay. Now the idea is to look at the width to look at the volume spectrum as a function of a t. So let's look at the function. Let's look at the function t of m with respect to g of t is continuous. And this is a continuous function. This is because of lemma 1. And moreover, the image lies in the set so the set this is the set of all areas of sigma with respect to g of t, where sigma belongs to is an admissible varifold. And now the crucial thing is that this set a priori would depend on t, but because all minimal surfaces are the same, the set is not changing with t and is just equals to this set. And moreover, not only the image does not change with t, as this set is countable because this set is countable, which is a countable set. And so if you have a continuous function whose image lies in a countable set, the function has to be constant. So does t, the width as a function of t is constant in t. Okay. But now this contradicts the Weil law, because the Weil law says that the p width grows like the n plus 1 root of p times the volume, and because the volume of g epsilon is bigger than the volume of g, then the function cannot be constant. On the other hand, the volume of m with respect to g epsilon is strictly bigger than the volume of m with respect to g. This is because phi is not identically 0 and non-negative. And so this implies that, and so the Weil law implies that there exists some p in n where the p width of m with respect to g epsilon has to be strictly bigger than the p width of m with respect to g, and this is a contradiction. Okay. Okay, so let's see. Okay, so let's just stop here for 5 minutes, and then I'll state the equidistribution. I'll state some conjecture, and then I'll outline the proof of the equidistribution. Is that okay? Yeah. Okay. So the goal now is to prove the following theorem. So this is joint with Fernando, Antoine, and myself. And the theorem is that, again, assume n between 6 and 2 is then the statement is that for a C infinity generic set of metrics G, there exists a sequence of closed minimal embedded embedded hypersurface with respect to the metric G, such that for every continuous function, we have that the limit of I sum the first q elements of the sequence. Yeah, so the elements there are taken to be closed, embedded, connected, minimal surface. Such that if I sum their integral over the first q elements, I divide by the total area. And the limit of this is going to be the integral of f divided the average of f on the ambient manifold M, and we just denote this by like this, integral with a cross. Okay. Actually, what we proved, so we state this result as saying that for a generic set of metrics, you can find a sequence of embedded minimal, closed embedded connected minimal hypersurface that is equidistributed. So more generally, the thing we prove is actually a bit more general than this. We prove this not only for functions f, but also for trace of tensors, of symmetric two tensors. So I'll just state this, that the sum, when I goes from 1 to q, the integral of sigma I of the trace of h with respect to sigma I divided by the sum when I goes from 1 to q over all the areas. This converges as q goes to infinity to n over n plus 1. And now we have the average on M of the trace with respect to the metric G of h for all h symmetric to tensors. Okay, so let me make some conjectures about what should we expect in the strongest possible version. So the first conjecture would be that for a C infinity generic set of metrics, we can find some sigma p. So what this is, if you recall, this is a stationary integral varifold whose support is a smooth compact embedded closed minimal surface. So we denote by this, so that they realize the width and for this we have that the integral of f over, if I average a function over sigma p and I make p go to infinity, I should obtain the average of the function on the ambient manifold. Okay, so what this version is saying is that if we look at the stationary variables that realize the width, they are becoming equidistributed. Okay.
But
yeah.
I don't know.
Yeah,
I
yeah,
mean, my bet is that rather than relying on generic, I would rely on positive Ricci to have a statement like this, right?
In the our intuition is that as p goes to infinity, this sigma p, if you take a ball of say a tiny radius on any given manifold for a generic metric, as p goes to infinity, if you look at the intersection of that ball with sigma p, you won't be able to know whether you are on positive Ricci or on Euclidean space or on another ambient manifold. So as p go to large, the behavior of the sigma p should be low. I mean, they should be, you should see something on one scale and then just gets replicated on all the other ones. I would expect that you get this statement even without, for generic metrics. That would be the expectation. I mean, of course, it's hard to know. It's hard to know in general because there's no single example in which we can compute this. But this would be the expectation. The other conjecture is that for equidistribution like this should hold for every metric and every dimension, regardless whether generic or not. So the theorem should hold without generic assumption, generic condition, and dimension assumption, and dimension restriction. Dimension restriction. So there's an important question. We don't put this as a conjecture because we have no, this is an open question, is whether this minimal hypersurface should become equidistributed on the Grassmannian. So that is unclear. So this is a question open. Do sigma I become equidistributed on Grassmannian? So this statement suggests some form like this, but this statement itself does not seem to give equidistribution. But actually, I have no. I would love to see evidence both ways. Either way, I have no strong feeling about this. So let me now. I will recall. So Fernando and I, we got a lot of heuristic. We got a lot of motivation at looking at what happens to the problem of the eigenvalue for the energy. And so so for instance, the Viola for the volume spectrum, that also occurs, of course, for the standard spectrum of the energy, but also there's a theorem proven by Uhlenbeck who says that for generic metrics, the energy spectrum, the eigenvalues are all simple. That was one of the motivations to make the multiplicity one conjecture, which says that for generic metrics, the width should all be simple, meaning realized by a multiplicity one things. And there's these statements of equidistribution, they also appear in some way or another in the context of eigenvalues. And so I will just put I will write some results about it. I have no concrete evidence why this should be important more than just they seem to look the same, and they also given by a min-max characterization, but that the techniques to prove this seem to be completely different. So let me show you some statements. So this is a similar setting, which so far has been a good source of intuition. Okay. So here I take n+1 manifold, and we look at the energy eigenvalues. Lambda 1 less or equal than lambda 2, and so on. And we take phi j. This would be orthonormal basis of eigenfunctions. Functions. And so there's a construction here due to Zeldich. He calls these random waves, and is the following. It takes the span of all eigenfunctions, whose eigenvalue with the square root of the eigenvalue being between n and n plus 1. Okay. And so, and then he proves the following theorem. Zeldich. He shows that, now the first statement will not be completely precise, but you can check in the paper. I'll just write it. It's like this. For almost all sequence of elements, I call it psi n in Hn, then he has that the sum when k goes from 1 to n of 1 over k, and then the integral over the zero set of this element of a function f, it divides this by n. Okay. This converges as n goes to infinity to the average of the function for all f belong to C0m. So I think his motivation was the following. If we just look at the zeros of eigenfunctions, they might not. So of course it's a conjecture. I mean, it's part of Yau's. We took at the zero sets of eigenfunctions. There's a conjecture about how they should grow. In this particular case, if the eigenvalue is comparable to n, they should grow like n. So this is proportional to the area of that, conjecturally speaking. So the lower bound was, of course, proven by Loganov, and the lower and upper bound are proven in the analytic case. But if we look at the zero sets of eigenfunctions and divide by their growth rate, if we look at every sequence, they don't seem to satisfy a universal law like this. Okay. So Zeldich's perspective here is, instead of taking a single sequence, he averages all zero sets where the eigenvalue, the square root of the eigenvalue is between n and n plus 1, and this should satisfy, and this they prove to satisfy the following universal law. So in the same paper, he conjectures. So this is formally resembles a bit our theorem, and then in the same paper, he conjectures that for almost all sequence phi n in Hn, then he conjectures actually a stronger form of equidistribution like this. So almost all here are with respect to a measure that he puts on this space. Again, it's known that you can find different sequence of nodal sets, such as if you take this average, they converge to different limits. So almost all or some property like that is crucial. Okay. There's another setting in which the eigenvalues provide theorems similar to those, which is so let me write the following theorem. So this follows from the it's called local Vi law. Okay. So the statement here is that there exists a density 1 sequence of the space of all orthonormal of the base of orthonormal eigenfunctions, density 1 subsequence, density one sequence oh no, sorry. Okay, sorry. So I was writing the wrong statement. So let me just write the true one. Okay. So the statement is sorted. Is that just the sum when I goes from 1 to n, and if I integrate the ith eigenfunction against the function f, and I divide by the total measure, which in this case is just n because these are normalized, this converges as n goes to infinity as the integral of f m for all f ambient function. And what Coulomb, Verdier, Schnirelmann, and Zeldich, their combined work, what it shows is that you can get a stronger statement when you have some negative curvature hypothesis. So let me just write this. So this is due to Coulomb, Verdier, Schnirelmann, and Zeldich. Is that assume that the geodesic flow is ergodic, as the ergodic geodesic flow. So for instance, this is assured, this is satisfied if you have negative sectional curvature as the ergodic geodesic flow. Then what they showed is that there exists a density one sequence of these bases of eigenfunctions such that if you integrate this against a function m f, then this converges as j goes to infinity to the average integral of f on m for all f in 0. Okay. So this I put this statement here because this gives I erase it. Oh, okay. So it's true. I mean, it would be the equivalent of this conjecture, but I would expect this holds for just bump is enough. We shouldn't need no curvature assumptions there. Okay. So what I'm going to do now is I will briefly outline the proof of the theorem. Is this? Yeah, sure.
That theorem that be true for all metrics or for
For the local vi law, yeah. I think it's for all metrics because if you do the sum of the squares of the first eigenfunctions, there's a formula for that. And so this just follows from integrating that. Yeah. There's a formula for that. It's like lambda to the n times some universal term plus lower order. So this just follows. We check that. We check that, and we seem to give. That's right. Yeah, we seem to give the same thing. Yeah, yeah. We checked it at some point. Yeah. Seems to recover that. Yeah. Okay. And any more questions? Questions? Okay. So for every sequence there. So that's okay, so there's an important conjecture here that a lot of people actually at the Institute work on that. It's called the quantum-unique ergodicity conjecture, which says that under the same assumption, we don't need to take a density one sequence, meaning any subsequence of the eigenfunctions will satisfy this. Okay, any subsequence. And this was checked in some hyperbolic surface and in cases of increasingly generality. And it's known that without the ergodicity assumption that the convergence for every sequence it's not true. Okay. So there's a lot of work on this quantum-unique ergodicity conjecture. Okay. It's due to Sarnak and someone else. Yeah, I apologize. I don't know his name. Yeah. Okay. Okay, so let's sketch the proof, tell you some key ideas. So of the proof. The proof is some very technical aspects, so I'll try to simplify and ignore many of the technical issues. Okay, so the proof is not so crude as the one for the density. Okay, but I'll show you a key computation. Okay, so this is a key computation. So the goal now is to try to understand the proof of that. So let's take G symmetric, and suppose we take n functions, and out of these n functions, we can consider a family of conformal deformations of the metric G. So given a vector in a unit cube but centered around the origin, so we denote this. Okay, sorry. We can consider the following metric, G of t. So t is a vector here, is the exponential, the sum when I goes from 1 to n of ti phi I times g. So it's a conformal deformation of the metric G. And if we do this, then we can consider a function, let's call it psi p. This is a function from this unit cube into the real numbers. And the function is the following. Phi p of t is, the function is going to look weird, but then when I take the derivative, it's going to be obvious why this is a good thing to consider. Is the natural log of the p width with respect to the metric G of t minus n times n plus 1, the log of the volume of M with respect to G of t minus the log of p over n plus 1. Okay? So the reason why this function is worthwhile to consider is that because the y law and this lemma 1 implies that the function phi p converges to the natural log of a universal constant alpha n as p goes to infinity uniformly. So the uniform convergence comes from the lemma 1 that I proved on the previous hour. So this is a sequence of functions which converges was constant as p goes to infinity, right? So now let's suppose that the function will only be Lipschitz, but let's suppose that it's C1, that I can take derivatives with no problem. Okay. So in particular, now this is a big assumption. Assume that the p width with respect to G of t is realized by some integral varifold which supports a smooth, compact, embedded minimal hypersurface. We write this way. So this is always true, is the content of the min-max theorem. The big assumption is that this element changes continuously, t. So, and t to sigma p of t is continuous. Okay, suppose that this is the case. So if that is the case, then we can take the derivative of the width with respect to t, and so the formula we can. So the reason why we do this deformation is that if I take the partial derivative with respect to ei of g of t, this is just equal to phi I g of t. Okay. It's a conformal deformation, and so using this, we can see that the derivative of the p width of g of t, so this is going to be ti of sigma t of g of t, and here we have to differentiate two things. The area, so fixing the metric and differentiating the hypersurface, and fixing the surface and differentiating the metric. But the hypersurface is a critical point, so if I fix the metric and I differentiate that in that direction, the derivative will be 0, so we don't need to worry with that. We just need to differentiate with respect to the metric. And here the formula, I mean, this is a conformal deformation. It's an explicit computation. It's just n over 2 over the integral of sigma pt times phi I. And here would be the area element with respect to t. And likewise, this is also a standard formula that the volume of M with respect to g of t, this is equal to n plus 1 over 2 over the integral of phi I dv of t. Again, this is just a standard formula using that conformal deformation. And so if we put these two things and differentiate that function there, then we get this neat formula that dti of phi p of t is n over 2 times the average integral of sigma p of t of phi I. What? Oh, what is C, that's right. Thanks. It's this, the average of M of phi I. Okay. So now we see that we have a function who's converging to a constant uniformly, assuming it's, say, C1 with bounded C1 norm. Then we have the derivative is given by this expression, and so the derivative should go to 0 uniformly. And in this case, the derivative go to 0 uniformly. It means that the average of phi I on sigma p is just converging to the total average, which is the strongest possible form of equidistribution. Okay. And so so here this is property, let's call property A. From A, we should expect that the gradient of this phi p of t goes to 0 as p goes to infinity, which is just saying that the integral of sigma p of t phi I is converging to the integral of phi I as p goes to infinity. And this for all I goes from 1 to what I ranges to n, right? So of course, the big problem is that it's known that the function is not C1. So the function will only be Lipschitz, and so we cannot just take the derivatives like that. So this is the big difficulty. Okay. So let me do two lemmas that will allow us to do that. Oh, sorry. So let me write two lemmas here. Okay, so now so this was just heuristic. Let's prove the theorem. And we start with two lemmas. Proof. Yeah, sure.
Moving at a very heuristic level.
Yeah.
But can't you just sort of recycle this idea by using Rademacher's sphere? So you say, it's true almost everywhere.
So that's going to appear. So I will address that right now. Yeah, it's okay. Yeah. Okay. So, but let me just. That's a good question. So let me just give you one example. Okay. So still heuristically speaking, you can have a Lipschitz function who goes to 0 uniformly, but the derivative is always bigger, greater or equal than 1 in absolute value, right? So, the standard example is this one, right? Just
almost everywhere.
Yeah. So, and at the point, the derivative, if it exists, is always either 1 or minus 1, and the functional oscillation is going to 0, right? And so this tells you that, this tells you that surely this has to be interpreted accordingly.
Yeah.
Okay. Just use, it's differential everywhere, but at the point the derivative is always 1 or minus 1, is never close to 0, so you never get it. Yeah. So I'm going to talk about that now.
So the problem is not quite differentiability, but the fact that you can't really recover.
It's two problems.
That's
right. Yeah. It's They are somewhat related. Yeah. Yeah. Okay. So it would mean So you can imagine that continuous in varifold, but in the setting we will use, it will mean the following, that this guy is a sum of connected components, and each connected component varies continuously in the space of smooth emergence. Okay. Okay. So there is this important lemma, which is that suppose we have a map from a unit cube into the space of smooth matrix. Okay, and then the statement is that there exists G prime some C infinity perturbation of G such that for all integer p the following holds, such that for all the following holds. Let me write here. So that the function t sends to the p width with respect to g is differentiable almost everywhere. Well, as I said, this is just Rademacher's theorem, it's no big deal. But the derivative is related with minimal surfaces like this, that and the derivative with respect to any I component of the p width with respect, so this is like this, with respect to this perturbation, this is equal to 1/2 the integral of sigma p of t of the trace with respect to sigma p of t. And now this is the standard formula. Okay. Where I is any number between 1 and 1. And of course, the p width of is the area of this guy, and the index of sigma p t is always less or equal than p. Okay. So what it's saying is that you take a family of metrics. Of course, you know that the function is Lipschitz, so the function is differentiable almost everywhere. To get this formula, not only need to take, if you take this n-parameter family of metrics, you need to know not only that it's Lipschitz everywhere, but you also need to know that the metric is bumpy almost everywhere. And so because you need the metric, this n-parameter family to be bumpy almost everywhere, that you need to give it a tiny perturbation. Okay, because the initial smooth family the matrix might not be bumpy almost everywhere. So you do a tiny perturbation, becomes bumpy almost everywhere, and then the proof is still a bit technical. I'll just sketch the basic idea, and then in that case we can make sense of that formula there. Okay, essentially what it makes. Still, we have the problem that the derivative might not go to 0, which is a second problem. Okay, so let me just sketch briefly the argument. Okay, just sketch. Okay, so the first thing to do is to use transversality arguments to do a tiny perturbation of G so that G prime is bumpy almost everywhere. So the first thing is that transversality implies the existence of G prime perturbation of G so that G prime T is bumpy, meaning the minimal surfaces are always non-degenerate for almost everywhere T in the cube. Okay. Then the argument becomes simpler if we assume, for the sake of argument, that M admits no non-orientable embedded hypersurface. So let's assume, for the sake of simplicity, that M n minus 1 has no non-orientable surface. Non-orientable hypersurface. The reason why the argument becomes easier in this setting is that if G prime T is bumpy, then we can apply sharp compactness theorem to conclude that and Ti is any sequence converging to T. Let me write this. If Ti is a sequence converging to T, and sigma it is a sequence, sigma I is a sequence of stationary integral variables whose support is smooth, compact, and embedded, but with respect to the metric G prime Ti, then let me write all the conditions. The area is universally bounded. Let me write this. The area equals, say, some p width, and the index is bounded by p. If these three conditions happen, then there exists sigma, a minimal surface, minimal hypersurface with respect to GT, so that the sigma i's converge strongly to sigma, okay? And the area of sigma equals the p width with respect to this guy, and the index of sigma is less or equal than p. And then if we have, for this, if we have strong convergence, then essentially we can just do the argument there goes through. Okay? So then you can reduce to the smooth argument. And then you work a bit more, and then the rest is, then you just argue like in the smooth case. And then from here you can just argue as in the smooth case. And then you argue as in smooth case. And we then argue as in the heuristics case, where now you can make sense of it. Okay, of course, if the manifold admits non-orientable hypersurface, then you cannot assure this strong convergence because it could degenerate on something with non-orientable multiplicity. Okay, it's a bit more technical, it can still be done. So this is the, now there's a second lemma which is related with the question of Alessandro, which is that we have this function is differentiable almost everywhere. I have a good expression for the derivative almost everywhere. But the problem is that even if the function goes to a constant, it does not mean that the derivatives go to 0, right? And so the correct way to interpret this is in terms of convex ulls. So let me write here the lemma. So this is an abstract proposition. F, a function from a n cube into R, which is Lipschitz. And so let's define this. This is, in the literature, this is known as the Clark differential. So it's generalized derivative. This is the convex hull of all vectors V such that there exists a sequence Ti converging to T such that the gradient of the function f Ti converges to the vector V. So if the function is Lipschitz, I know that it's differentiable almost everywhere. I take some point T. I look at all sequence converging to the point T such that the function is differentiable at Ti. So the gradient is well defined. And then I look at all possible limits. Okay, and then I take the convex all of that. For instance, in this example, if I take this point, that generalized derivative is just either 1 or minus 1. But if I take this point, then the generalized derivative is the interval between minus 1 and 1. Okay. And so the statement is that there exists some constant just depending on n parameter there, such that if f of x minus f of y less or equal than 2 epsilon for all x and y in In, then we can find a point in the parameter space such that the distance between 0 and this convex hull is less than that constant c times epsilon. Okay. This is the weaker version of that. So let me sketch the proof of this. So let's sketch the proof. So the first step is to, if we assume that the function has interior maximum, then we see that this generalized derivative contains 0 in its convex hull. Okay. Is that suppose f has maximum at t bar in the interior of In, then if the function is C1, the statement is that there's a point that the derivative is 0. But if the function is only Lipschitz, the statement is that this convex hull contains 0. Then 0 belongs to like this, just like it happens on that oscillation. Okay?
You mean the interior of the cube?
That's right, yeah. On the interior, yeah. Interior. Sorry. On the interior of the cube, it has to be interior point. Okay, so let's see that. Okay, so suppose not. If not, if 0 is not there, then you can use Hahn-Banach to conclude that this convex set has to be contained on some upper F space. If not, then Hahn-Banach is just minimization, then use convexity. Tells you that there exists some vector v in Rn and some delta positive, such that this convex hull at the maximum is contained on a upper F space. So the picture is like this. This is delta, and this is the convex hull. Okay. So because convex, if it does not contain the origin, it has to be above a certain upper F space. And now, of course, without loss of generality, we can assume that if I restrict my function, just along the line given by v, that's differentiable almost everywhere. This function, psi of s, let's make sure I'm not calling, psi of s, which is f equal to t bar plus s v. This guy has its derivative equal to the gradient of f at the point t bar plus sv dot v. This almost all when s is very small. Okay. And now just follows from the, let's do it here. Okay. And so now, but from this condition, assuming this condition, from this condition, what we get is that phi prime of s has to be greater or equal than delta over 2 for almost all s very small. Because if I could find a sequence a sequence s size going to 0, where this is less than delta over 2, then I'll take the limit and I'll find a vector there which would not belong to this set, and this would be would contradict that inclusion, right? So we would just get this, and so of course this implies that phi has no maximum when s equals 0, which is a contradiction, because I know that psi has a local max when s equals 0. This is contradiction. Okay. So the first case is this one, and now the second one, you just reduce to this case by a perturbation. So let's see, we write this. So for the second case is choose some cutoff function, which is C1, and looks something like this, such that, so now let's draw. There is 1/2 minus 1/2, and the function should be here 0, and then 1, and 1 in the neighborhood. This is 1, this is 0, and this is the function eta. And then we can imagine that this is defined on a cube, but the important thing is that is 1 at the boundary and 0 in a neighborhood of the center of the cube, right? Then the remark is that then f tilde, which is f minus 4 epsilon times eta, must have interior maximum. Must have interior maxima. Okay. The reason is because this follows from this condition. It's easy to check. This follows from this condition. This condition implies in the fact that at the boundary the function is 1, so at the boundary the function is 1, in the interior is 0, so there has to be interior maximum there. And so by 1, so 1 implies that exists a t-bar, a point at interior maximum, let's write t-bar in IN, okay? So from 1, I'm going to write this. So from 1, this implies that 0 is in the convex, is in this generalized derivative of f tilde t, but because this guy is differentiable, this just implies that the distance between 0 and this is greater or equal, less or equal than some universal constant. It just depends on the derivative of this times epsilon. So we do it. Okay. So now we have so we know that we can differentiate almost everywhere, and then we know if the function is small, that the correct thing is not to say there's a point that the derivative is small. The correct thing is to say that there's a point where 0 belongs to the convex hull, and then we can deduce the theorem from that. Yeah, okay, so I'll just do that very briefly, and then I'll stop. Okay. Okay, so we have all the ingredients now. Yeah. Okay, so proof of theorem. So there's one piece more of notation, which is justified because of these generalized derivatives. So let's just denote by convex of nu g. This is by definition all convex linear combinations of elements which can appear as width of manifolds. So this is just the sum when I goes from 1 to L of alpha I sigma I over sigma I, such that sigma I is a stationary integral variable. The support is a nice embedded minimal surface. The sum when I goes from 1 to L of the alpha I equals 1. All the alpha i's are between 0 and 1. It's a convex linear combination. And I'm seeing this as a subspace in the set of all unit Redel measures. So this is contained in the space of unit Redel measures. unit radon measures. Where when I denote this, what I mean is the measure you get by integration over sigma I. And then if I divide by the total mass, this is a unit radon measure. And then if I do a convex linear combination, that's still a unit radon measure. Okay. Okay. So the proof in the paper is more delicate because we do it for tensors, but if we just do for functions, at least the formalism gets simplified a bit. So let me just do that. So let's choose a space of smooth functions which is dense in the space of continuous functions. We can do this because this space is separable, because M is a finite dimensional space. Okay. And now let's just denote M of n. This is the space of all metrics, smooth metrics, for which we can find a measure on these convex linear combinations of embedded minimum hypersurface with multiplicities such that if I evaluate this measure on the first n elements there and compare with the total average, this is less than 1 over n for all I goes from 1 to n, and the support of this guy is non-degenerate, and the support of nu is non-degenerate, because the support of nu is always the support of nu is a union of compact embedded minimal hypersurface, and I just require that to be non-degenerate. All right, with respect to G. Okay. Okay. So like before, this set is open because of the non-degeneracy condition, and this is a strict inequality. So it's not hard to see that the set is open. What we want to check is that the set is dense. So let's do proposition. Is C infinity dense. Okay. So the first remark is that because of, let's see, it was lemma 2, this condition can be ignored, because if this condition is not, if I have an element which belongs there, but this condition is not satisfied, then I can do infinitesimally small perturbation of the metric in C infinity such that the support of this guy will become non-degenerate. And so if I call this condition H, then the first is that lemma 2 implies that this condition can be ignored. Condition H can be ignored. Okay. So now let's take some metric G, and let's take some number delta, and now we're going to do a deformation like we had in the heuristic argument. And so we take G I n into the space of smooth metrics, and the deformation is G of t is the exponential, the sum of ti phi I times G, but now I want to be a tiny perturbation, so I put the delta in front there. Okay, something like this to make it small. Sorry. Yeah, like this to make a small perturbation. Okay. Yeah. Okay. So now we want some t bar in the cube such that G of T bar belongs to that space. So this is what it means that it will be dense. So I'll just find this. So let me just find this T bar, and then I'll stop there. So like before, we consider this function. That function we had considered before, minus log of p over n plus 1. And now let's make a big simplification, which is now what I should do is I should apply lemma 1 to this family of matrix G and get this family G prime, and then do everything with respect to G prime, and then just make sure the error disappears. But let's just assume that lemma 1 applies to the original conformal deformations G. So let's assume, so no need for the G prime. Let's just assume that. Assume lemma 1 was lemma 3 applies to G, to the family G of T. Okay. So now let's fix epsilon positive. So the Y law plus lemma 1, this implies that there exists some integer p such that this function psi, the oscillation of this function, is less than 2 epsilon for all xy in the cube, right? And so if this is true, then the lemma 4 implies that there exists some T bar on the cube such that V belongs to these convex linear combinations of derivatives of this function psi t, and the norm of V is less than C epsilon. Right? But now if we combine with the formula for differentiating this almost everywhere, and here we have to use some more arguments, so let me just write this here and then I'll stop. Okay. Just so that we can finish. So now that if we take this V, you can check that V dot the ith component is equal to delta n over 2 times, can check that there exists an element on these convex linear combinations of these measures such that if I look at the ith component of the vector V, where the vector V is the one that belongs to the convex hull there, then this is what we get for all I goes from 1 to n, right? And so in particular, V less than epsilon just implies V less than epsilon, what did I write? C epsilon, yeah, sorry. V less than C epsilon implies that nu phi I minus this guy, the absolute value, is less than C epsilon 2 over delta n. And now we can choose delta smaller than epsilon, much smaller than delta, and just depending on this constant C, where this is less than 1 over n. This is by choosing epsilon small. And out of this, which implies that just GT bar belongs to the set Mn. And then we take M to be the intersection of all open dense sets, and essentially we show that there's a sequence of convex linear combinations of, there's a sequence where they're right. So then if we take the intersection of all mn's, we get that the volume measure is in the closure of this space, and then using some arithmetic properties, we can deduce from that statement there. Yeah, so I'll just stop here. I apologize for not finishing.